And I'm going to start from scratch with nothing else installed than the Elm compiler. That's the only thing I'm not going to show, but it's basically just a binary that you download for your platform. And I'm going to go and make this deployable right away. So I'm actually going to go to my own to my repositories, start with an empty repository, and then we're going to actually deploy this to GitHub Pages right away. So I love that GitHub is now proposing these awesome names. So we're going to go with Supreme Octolamp. This is going to be our repository, and we're going to create a directory of this name. We're going to quit out of here, go into my Elm folder, make dir, boom, go in there, and then we're going to execute. Well, actually, what am I going to do? I'm going to git init. I'm going to create a dist directory, the distribution. That's where our files that we're going to deploy to GitHub Pages are going to be. So let's do this. And we're just going to echo HTML body hello body HTML into an index HTML that is in this directory. So it's dist index.html. So if we do tree here, then we see that's what we have. That's great. We are going to add this ci minus commit message initial commit, and then we're going to do all of this. Bam. So that means if I refresh here, I should now see this initial commit with the directory. Perfect. So now we are going to activate GitHub Pages, from this repository, and browse user suggested browse flow. I think no, that's not what we want. GitHub Pages, pages, action, and I think it's this one. So yeah, that's one that's from GitHub itself. It's maintained, and I think there are some examples somewhere. Starter workflows, exactly. So we're just going to deploy static files. Of course, we could choose to also compile our Elm in GitHub Actions, but I'm leaving that as an exercise for the motivated YAML editor viewer here on the stream. Okay, let's do a directory that GitHub expects our workflows to be in. That is a hidden directory called GitHub, and a workflows directory in there. And then we are going to edit a deploy.yaml file, pasting this here. And so there's a bunch of things. Our branch we want to watch is main, and then permissions. I'm assuming this is all necessary stuff that I don't actually need to touch. We're going to check out. We're going to upload artifacts, upload entire repository. Here we want to say this is only the dist folder. So let's see how far we get with this. Going to add this, git ci minus m, add deploy action, and pushing that. And we're going back to our repository. We are seeing that one action is running. That looks already very, very promising. What is this thing doing here? So, green check mark, I'm assuming that succeeded. So let's go back to our settings. Refresh here. That did not work, or did it? Oh no, we have to go to the pages page, and here we see your site is live. And I already like have my DNS entry mapped in GitHub, so every time I launch a new repository, it basically gets a sub page under my blog, and we see hello. That's pretty awesome. So this is all that it takes to deploy some static HTML to GitHub pages, which is pretty awesome. So without further ado, let's start an Elm page or an Elm application. And so where do we start? Yeah, we're just going to copy the hello world example basically from the official Elm guide, and we're going to first we have to run Elm init, and this will create with an Elm JSON file, which is kind of like, if you come from the Ruby world, it's kind of the combination of the gem file and gem file log, because it contains both your direct dependencies and your resolved indirect dependencies. So if we do tree now here, we see we have a source file that is empty, and we have an Elm JSON. So now we are just going to edit an Elm module, a new one. We call it main Elm. I call it main Elm, but could basically have any name. Source main.elm, and we're going to paste this here. And for the sake of this exercise, I'm using LSP, and I'm using an LLM to help just do the grunt work, but I'm going to disable both of this here. Codium disable. Boom. So the LSP is still active. I can use it to like give me insights about the functions I'm going to call or add my imports, but I'm just removing the noise of the diagnostics, especially since I am not using any type annotations. I don't want it to warn me every time I'm missing one. So we have an Elm application, or actually I'm missing the module declaration here. Module main exposing main. And now we're going to use the Elm compiler to actually, what was it called? Our repository Supreme Octolamp. Supreme Octolamp. Where are we here? Tree. Elm stuff. Yeah, the Elm has like a hidden directory basically. I never need to look into this. You've been using Elm for over 10 years now, I think, and I've never had to actually look into this directory. So actually we're going to ignore this right away, because we don't want to check this in either. Elm stuff goes into .git ignore. All right, and now we're actually going to, so if I just execute Elm, of course we get a bunch of helpful information of what to do with it. We have a REPL, we just used Elm init. We have also this kind of live server, what I'm actually not using this. But what I'm going to use now is Elm make to actually turn the Elm code into JavaScript code. Oh, and I see Radan actually has joined the channel, has joined the stream. Thanks for tuning in. Now I'm twice as nervous. But yeah, as I said, like, I think I'm pretty tight on time, and that's why I'm probably not going to consult the Ruby solution a lot. But maybe I do a review and a follow-up stream, a comparison between the two solutions. All right, let's compile this Elm code. Elm make. We're going to specify the name for the output JavaScript file. It's going to go into the dist file folder, into a file called main.js. And now we have to specify which Elm file to compile. It's going to be the main rs. So if we say look into this head dist main.js, then we see like this is a bunch of JavaScript code that I also never had to look into for all of my Elm hacking so far. So the next question is, of course, we cannot just open the JavaScript file in the browser. We need to kind of embed this in the HTML, but luckily there's a section here in the guide, in the Elm guide as well, JavaScript interop, and basically we just did exactly those steps. We compiled it, and now we want to embed it in HTML. So again, I'm just going to grab this code from the guide, and we're going to open the index.html and replace it with this. So that means if I open the index.html, hopefully I'm just seeing this running Elm application, and here we are. I'm just going to open console as well here to see what's test to say. We're in works mode, so maybe we add a doc type declaration to our index.html. Boom. Going to reload. Now this is gone. That's great. Compiled in dev mode. So yeah, the Elm compiler has this dev mode, and for better performance, you can call the Elm compiler with additional flags to compile a more optimized version of the JavaScript code. All right, so maybe we just deploy this. What do we have here? We have our modified index.html. We just added the git ignore to ignore the Elm stuff. We have our compiled main.js, the Elm JSON, and our source. So we're just going to add everything. Git CI, MVP, git push. So now if we go back to our, we don't need this one anymore. No, actually one of those, like, let's go back to GitHub. Supreme Octolamp. In the actions, we should see, yes, our commit is compiling, or deploying, I should rather say, because there's nothing compiling actually in there. And this is our local version. I'm just going to move this here to not lose sight, and then we are going to move this deployed version all the way to the right so that I don't confuse them. How are we doing? This has run. Let's refresh here, and now we have a deployed Elm application in production in less than 20 minutes. That's not bad, I would say. Okay, but now for the real stuff. Let's do some Minesweeper. So here's our main application. I don't want to give an introduction of how Elm works. I'm just going to run really fast through it because the syntax is very different from usual frameworks. But basically, if you're familiar with React, Elm solves similar problems, but it also includes its own language and state management. So if you do React, you usually have to pull in Redux or manage your application state in another way. But basically, an Elm application always has all of this included. And with the main function, basically, we give a few functions to the Elm runtime to manage the state and the rendering of our application. So let's call our game state is initialized currently in this very simple game of counter. Our game state is just a number. That's why we initialize it with 0. And then we have the view function that we give to Elm as well, which receives our game state, which is called model. And then it renders a DOM with pure Elm functions. So we create a div, and the children's, these empty brackets here are the attributes. So this div doesn't have any attributes. And then we have 3 children in this div. One is a button, another div that displays the number of the current game state, and then we have another button. So if we inspect this here, let's hide this console and increase the size, then we see that's exactly the structure we have created here. And so from this view, we can issue messages. So we have one type called message that enumerates all the possible messages. In this case, it's just increment and decrement. And so on the press of the respective button, we basically issue this message, and then we give to the runtime environment from Elm, we give also an update function, and the update function receives two arguments. The first one is the message that was issued from the view, and the second one is the previous game state. And then we can calculate a new game state based on the message that we receive. That's basically how every Elm application works, and we're going to slowly basically blow this up to be a running Minesweeper, hopefully. So first of all, of course, like it's very common in Elm to think like data-driven or data structure-driven. So not surprisingly, I'm going to think of like what's my game state is going to be, because obviously a single number is not sufficient. And I would say we want to have some kind of board, of course. And this board can have either empty fields or bombs. So I'm going to first create, I promise that's the only few type related things that I'm going to do. One of the few types that I'm going to introduce. One is our field content, and it can be either empty or it can be a bomb. So this, and then our of course I could now directly search for a data structure that is kind of like a grid thingy, but in the end like and you would see in a minute, actually there's a neat trick with HTML and CSS that we can do. So I'm just going to store all the fields in one continuous array. So where's our init function? Actually, I'm going to create an init function here so that we have a bit more wiggle room. So we're going to say list.repeat, and you see this is the signature. I can quickly introduce you how to read a signature in Elm. So you see there's a lot less parentheses and commas going on than in conventional languages. So basically the last term here in this declaration is always the return type. So the repeat function returns a list of A, and A is a type parameter because it's like a generic type. So it the repeat function, as it's declared in the core library, doesn't know which lists we're going to do, but it can create any types of lists of the types of elements of any type. So the other things before the return type are basically the other arguments. So it's a function that takes two arguments and returns a list of A. The first argument is how many times we want to repeat, n copies is the first one, and then what value we want to copy. So we are going to start with an empty board. So we are just going to return empties. The first parameter was width times height, and the second parameter is what we want to repeat, and it's going to be empty. And so we want to give this width and height to this function. So when we're calling it, we don't need the brackets or the commas. We just say we want to have a 10 by 10 field. And so now we can actually see, before we move on, if this still compiles. Let's see. I already made a mistake. The init function expects one argument, but it got two instead. Why? Yeah, because it's actually, I declared this as a tuple, so there are some brackets and commas after all. And now what it tells me is like, because all these three functions that we give, the init, the update, and the view that we give to the Elm work with the game state, like it expects the type of the game state to be in the same shape for all of these functions. And we just said like our init function, actually the init function returns a game state of the type list of field content, but our update and view functions still work based on the assumption that this is a number. So we have to update those as well. So let's just not do anything here. Let's reduce these messages to one single no-op for now. And then this should just work. And here, of course, we cannot call from int, which converts an integer into a string. We cannot call this with a list of our field content. So we're actually going to throw all of this away. And we're just going to call list.map, because this is now actually the fields. And we're going to create a view field function that renders a single field, and we're going to give it all the fields. And now we're going to write view field with field, and we say if field, well, it's a case statement, but basically what we're doing is pattern matching here. So if it's empty, then we're going to render a div with a text with a hyphen for now. And if it's a bomb, then we're going to render a div with text, whoops, closing bracket, and we are going to do a bomb emoji here. Bam. So is this compiling? This compiles. But if we refresh, no, actually, yeah, it works. We see what we expect. We collapse this. We just see a list of 100 diffs with a hyphen inside there. So now I do the HTML trick or the CSS trick, which is I'm going to put a style block in here, and then we're going to use the grid layout to actually turn this list into a grid. So let's say we call this board, then we do display grid, and then I always forget the syntax for this. So I'm always consulting MDN grid template column something something. Exactly. So, and there's something with repeat in here. Here, that's what we want. So let's steal this, we paste this in here, and basically we say like every n elements, or a column, a row has n columns basically by using this repeat syntax. So we just say 10 and we say 2 em.
Viewers on iglebycollegejava.com/4w2.
First bot, of course, in the chat. Thank you. Goodbye. So now let's refresh this. This doesn't work because I haven't given the ID to our board yet. Where's our view function? ID, exactly. Auto import edit. Thank you, LSP. We're going to recompile and refresh. Now we have ID board. And now the question is, why does the CSS not apply? Here's our style, display grid, no. Or is it rows? Interesting. Did I not call it board in the CSS? ID board. Ah, no, ID, that's of course stupid, yeah. That's always the tricky thing with both like pair programming or streaming. If you talk and think, then sometimes you just cross wires and type and what you say and start typing what you think. So, awesome. Maybe we just give these a static height and a little border as well. So let's say height 2em and border 1 pix solid gray. Boom, refresh. Wonderful. That nearly looks like Minesweeper. So what you see, obviously, immediately there are no bumps. So I think that's something. Oh no, actually, something that I like to do is I don't want to manually trigger a compile, and unfortunately, the Elm Like it has this development server thingy, but since I'm working with my HTML as well, I always have to compile and to use it embedded in the index, and the uncompile doesn't have a watch mode itself built in, but there's like a cross-platform tool I really like using, which is called fswatch, that just can watch some files and then trigger a command line file. So I'm just going to watch this. O1 means it's only one event, because Elm stores swap and backup files and it triggers a lot of things. So I'm just saying, like, each time basically I touch it, there's only one event, and then I'm parsing it to xargs, which can take piped in arguments and kind of mingle them together with a command to execute. So again, we say like each line should execute that we pipe in there should execute one command, and then we just call the also we have to use this interesting thingy here that says, like, basically take the pipe thing and put it where the brackets are, but because I don't want to use it, I'm just using it to basically stash away, whatever I receive here in my xargs, because I want to execute basically a static command, which is Elm make output equals dist/main.js, and it's source main Elm. So that means if I change my Elm file here, just adding an empty line, then we see it's recompiling automatically. That is great. All right, let's add some bombs. So let's just say the last number in here, or maybe the first number, 5. That's the number of bombs. So where's our init function? Right here. So num bombs. So now, of course, we have to subtract the number of bombs from the empty fields that we generate. Bombs. But we also have to generate some bombs. So let's generate some bombs. And this is actually exactly the number of bombs, of course. And we are going to put both of those in both lists into a new list. And then we're going to call list concat to create the joint list. Num bombs, these nims, I have more typo. Oh, I really like to write bombs, apparently. Bombs, this is singular. Boop. Let's see. Ah, yeah, success. We compiled, so we can refresh, and we see we have, for some reason, empty fields here. I thought I put the bomb emoji in there, but I did not. So let's do this again. Bomb, puff. So refresh, and now we see the bombs are there. All right, that's a good first step. What are we going to do next? It's either like dealing with different visibility or actually shuffling this. So maybe let's do visibility first. So of course, this looks like the fully revealed field. Actually, let's do this here. That's more like it. And so basically a field can have two different states next to whether it's empty or has a bomb, which is whether it's visible or hidden. So I'm going to introduce one more type here, visibility, that is either visible or hidden. And now, instead of just returning the field content, we're going to return a record here, visibility equals hidden, content equals bomb, and then we're going to do this same here, visibility equals hidden, and like this can be further dried, of course, but I'm doing a lot of things that probably seasoned Elm developers would frown upon, but this is all like a speed hacking, golfing, whatever competition, so I'm not worrying about these things too much. And now, so we again changed what the init function returns as our game state. So of course our update on view functions have to be updated to deal with this new type of game state as well. So update function, we don't have to update because it doesn't do anything yet really. But our view field function receives now a field that has a visibility and a content. So now basically we can match on this, pattern match on this, visibility and content. So if, well, I think we can start right away with like, if it's hidden, then we don't even care about the content because we don't want the player to know what's under this field. So we just render an empty div. And so if it's, actually we don't need to specify this because this can basically be our fall through case here. So, and in this phase, if it is visible and empty, then we do the thing we did before. And if it's visible and a bomb, then we do the thing we did before. And in any other case, we just render an empty div. Does this compile? Visible, that sounds more like it. It compiles, so now we should see nothing. Correct. All right. Then I would say probably the next important thing would be to actually reveal things to make sure that that our rendering works. So clicked field is our message that we can issue from our view. So now we say, like, if we are in this hidden case, then we do on clicked field. And the problem now is, of course, we don't know which field is clicked if we just say clicked field. So we have to give this this constructor of this, or this message, an argument of type int. Since we just have a list, we can just say like the first field is the first field and everything has consecutive numbers. So now we just need to give this clicked field also the index. Let's call it idx, and currently, as you can see, we don't get an idx anywhere, so we are going to give this view field function an extra argument, and luckily we have a function called index map, which expects exactly a function with the signature. So if you look at the signature, index map is a function that takes two arguments, a function, a list A, and returns a list B. And the first argument of the index function, the mapping function, is one that receives as first argument the index of the element that we are mapping over, and then the element itself. And then we can specify how we turn this into a div in this case. So does this compile? No, because we still have this no message in here in our update function. So we are going to replace this with clicked fields. So now it compiles again, but it doesn't actually do something when we are clicking here. So what we want to do, the model, let's call it board. I want to update this board. This board is a list of fields. So what we're going to do is we are going to reveal the field list.map. We're going to reveal. We're going to map over all fields, and we're going to turn hidden into visible for the field with the index idx. So we're going to write this function as well. Well, reveal, and it takes an IDX, and it takes a lot of fields, and we're going not true. It takes an IDX. That's all. And then we have to use the indexed map as well. So this is current IDX, and this is the target that we're giving it. And actually the target comes first. And so we say if target, and this is not the current, and we get the field itself, of course. So yeah, let's look at the signature of indexed map again. The mapping function is our reveal function, and it takes the current index and the field and turns it into a field again. So why do we have a third parameter? Well, because we need to know which field to update, and this is where we use what's called partial application. So we take the reveal function and give it only one argument, although it expects three, and we get as a return a function that only expects the last two arguments. So if target equals current index, then then this field is actually a tuple of this and content. Then we return visible and content, and else all the other fields we just don't. We can do this smarter. Let's continue calling this field, and we just say field.content, and here we say we return the unaltered field. Does this compile? It does not. Content, why is it not content? Visible. Because it's not a tuple. No, we can use the record update syntax. So we take the field, that's much cleaner anyway, and we say visibility equals visible. There we go. And now it compiles. So that means if we refresh, we should be able, but we are not able. I know our empty fields are really truly empty. So let's actually say a text question mark just for now here, so that we are able to distinguish between those question marks. And now we can actually reveal our bombs. Awesome. Good stuff. Good stuff. All right, I think now it's time to shuffle the board. It's a bit too predictable. And this is also something that people from imperative languages struggle with in the beginning, random numbers in pure functional languages. Let's look for a package called random. And so we cannot just call a rand function like in JavaScript or Ruby, because all functions in Elm are pure. And pure means for the same inputs, you always get the same inputs. Like, so if we have a random function and we get different numbers each time we call it, it's not pure. So it's basically not modelable in this world of pure functions. And that's why Elm has something called commands and subscriptions, and they go on explaining this, of course, here as well. Their example here is how to make HTTP requests, which are also not pure in the sense that, of course, an HTTP request can return something else each time you call it, or fail entirely. And the number one thing we need to do to be able to issue commands which enable us to generate random numbers is we have to change from browser sandbox to this slightly more complicated browser element Elm runtime. So let's start by doing this. Element, and the main well, there's a couple of more or less obvious differences. One is we have to have subscriptions, and we don't need subscriptions from Minesweeper at all. That's why I'm not going to go into detail what those are. And it just gets a function that does nothing here. We have no subscriptions, sub.none. And the other thing is that the signatures of the functions of our init and update function are slightly different than before. We don't just return the game state or model as it's called in the world, in the Elm world. We also return a command, which is ultimately what we want to do. But before I show how we actually leverage this, I will just make sure our application actually compiles again without actually issuing any commands. So here we are calling init, and we are returning command dot none. So we're returning a tuple. This is the syntax for a tuple. See, this here loading is our game state in this particular example. And the second, the HTTP GET, is the command that we're not issuing. But you see also this init function takes this weird nothing parentheses here, and those are the flags. So flags are information that we can pass from our JavaScript world into our Elm application on startup. So I'm just going to take our tuple of number of bombs, width, height here as a parameter. I'm going to expect this. So we are going to write it num. Oh yeah, can I just... Yeah, actually let's just modify our init function. That's more readable, I think. So we are just going to remove this tuple altogether, and we are just going to... Our init function actually already expects this tuple. So that's already great. The only thing we have to change here is we have to also return a command, which as I said, is going to be nothing for now. And then we have also to return a command each time we can return a command each time we update. And since I don't want to return, well, I'm just going to do this here, right here. Not a big deal. Command dot none. So are we compiling again? We're compiling again, and now it complains that the flags given to your Elm program are undefined, which is correct because we haven't altered our index HTML. So let's change this. We go to our init function here and we call flags, and the way to pass tuples to Elm is through a JavaScript array, because JavaScript doesn't have tuples. So we say 5 bombs and a 10 by 10 grid. Going to save this. Of course, it doesn't recompile, but it works again. So nice. So that means if we want to do a smaller array, we can just change the call in our index HTML. So that's pretty good. So maybe we just, for shits and giggles, we just deploy this. This looks all good. Git CI init board from JS. To push it. I'm going to bring back my watcher here. Let's see what our actions is doing. Init board from JS. So how long do these tasks actually run? 30 seconds. Okay. In progress. That's great. Here's our... You see, I can show you. I can try with my new automations here, but I can show that actually I am on my production page here. And let's see if that was enough for GitHub to run. Yes, so we can refresh here, and now we have a slightly more Minesweeper-y JavaScript application live on my blog. Awesome. Cool. But of course, that's good progress, but still a long way to go. So now I said, like, all these changes I made with these weird commands, how do we actually leverage this to get random numbers? So my ideas of randomizing this is I don't want to calculate complicated new random position XY. I already have a list, so I hope that I get some way from Elm to just shuffle a list. Unfortunately, here in the Elm random package, there's nothing like this. But if I say Elm list shuffle, I hope here random list random extra. So there is a package from the Elm community. Shuffle the list. Wonderful. Takes, oh, I don't care because I have extremely short lists. So we see like list A, and it returns this weird generator thing. So that's the construct that gives us ultimately the command. So we see in the original in the core random. Well, it's not core. In the random package, there's a function called generate. And it takes some weird function that takes something and makes a message. But most notably, it takes a generator and it gives us a command. So somehow we have to bring together generate and shuffle to do all this. So the first thing we need to do is we have to add these two packages to our Elm application. So I'm going to interrupt my watcher here, and then again a thing. If you have Ruby here, you would probably use bundler or gem install. If you have React or JavaScript applications, you use npm. But again, for Elm, the nice thing is I don't have to install any other tools. The Elm executable is not only the compiler, but it's also my dependency manager. So I'm saying Elm install Elm random, and it says like, oh, I want to modify your Elm JSON. I'm going to add this to your direct dependencies. Yes, please go ahead. And while we're at it, we're going to do the same thing. I'm just going to grab this string here from the top and say Elm install bam random extra. Yes, please. And now actually I can give you a quick diff here. Our Elm JSON was modified. So if we say Elm diff, then we see like in our direct dependencies, it added these packages for us. Awesome. Bring back the watcher and import random. We're going to say we want to use the generate function without having to specify which package it's from. That's what the exposing part is for. And we're going to use the random.list module, and we're going to use the shuffle function from this. So let's recap. We want to, when we start our program, we want to basically shuffle the board directly. So what this means is we can use the fact that we can return a command from our init function to do the shuffling for us. So what gives us the command? That's the generate function from the random package. So we are going to call this, and then we're going to try to figure out the arguments while we're there. So we say generate. Weird message thing. I'm just going to skip over this for now and use the parts that we know about, because we know we have a generator. Our generator is our shuffle. So our shuffle, which is in fact another function. That's why I already started with the open bracket, because I know I have to give this shuffle function an argument, a list of A, which is our unshuffled list. So Let's call this unshuffled. And then we can do some local bindings here, unshuffled, and I'm just going to basically this list that we calculated before, I'm just going to name this unshuffled here. Fix the indentation a bit. I could use the auto formatter, but I'm deliberately staying away because the default Elm has a very opinionated way, as it has an extra tool called Elm format. That's one thing that the Elm compiler doesn't do for you. So the Elm community has an opinion, a global opinion about how Elm should be formatted, similar to Go format, but it's a very white space, rich formatting, and since I'm trying to stay under 100 lines here, I don't want to just use this just yet. So basically, I don't care for my first game state because I know I'm going to shuffle it anyway, so I'm just going to put an empty state in here, and then I'm going to shuffle the unshuffled. So generate, we have the generator A, I believe at least, shuffle. Yes, we have a generator for list A. And so this A after the generator here, that's the same type that this other function that I haven't specified yet expects as the first thing. And so what this basically does is says the function generate, the generate function takes this generator of type A and says like, I'm going to give you a command that when it is executed is going to send a message, the same thing that we are sending from our views. And to do that, you have to tell me how to turn the generated thing A into a message, which is not surprisingly exactly the signature of this function that we're expecting here. So I have to give it a function that takes our shuffled list and turns it into a message. So let's create a message that expects a shuffled to receive a shuffled list. Get shuffled fields. And what are these? List of something that has a visibility that is not the visibility that I wanted. Go away. And what's the other thing? Content. Content is field content. Bam. Does this compile? No, because I still have my dot in here. And now the magic of these type constructors. So these things that are separated by this pipe symbol are type constructors, and they are also functions, because what they do is if I give an integer to this clicked field, I get an object or a value of type message, if you will. And the same is true for this got shuffled fields. So if we say got shuffled fields in here, what did I do? Got shuffled fields. So let's read this again. So the generate function, let's start from the back, takes the generator shuffle, that if we give it a list of our fields, then returns a shuffled, then returns a command, the generator returns a command that is executed later by Elm, and then we'll call our got shuffled fields constructor function, which happens to receive a list of fields. So let's see if this compiles. No, because I'm missing some parentheses here. And now we see we created a new message, but we don't deal with it yet. So it's another help that we get from the Elm compiler to make sure that our program actually runs. It says like, if you introduce new messages, you also have to update your update function to say how they modify the game state. So let's go here in our update function and say got shuffled fields. Here we have the fields. And then we just return the fields that are now shuffled. Is this correct? No. Because we have to also, because we're in the update function, we also have to return a command. Command.none. Boom. Now it is compiling. So that means if we refresh and we uncover these fields, the bombs are gone, and they are, I don't know where. So for non-Elm programmers, I would say this is probably one of the most challenging things in this challenge of creating a Minesweeper clone. But yeah, as I said, I don't know how many bombs did I say? Didn't I say 5? Are they all? Wow. Look at me, I can play without the numbers, nearly. All right, we have the shuffled fields. That is pretty good. All right, the next thing that is obviously missing are the numbers on the revealed empty fields that indicate how many surrounding fields have a bomb on them. So let's do that next. And of course we could calculate that each time we click a field, but I think it's probably more straightforward if we just calculate that once. After we shuffle the bombs, we just calculate the numbers, and then we just have to deal with revealing them. So the first thing that we need to store a number on each of these fields is next to the empty, we have to store an actual integer that tells us how many fields are there. And so before making it too complicated on ourselves, let's do small steps. We just introduce this new argument for the empty state, and then we fix all the places that break because we're not dealing with this new argument. First one is in main, line 47. Let's go in line 47. Here, if it's empty and we have an n, then we just render this number. So we say everything is strictly typed and there's no weird automatic conversion or auto boxing, so we have to be very explicit. We say from int function that turns an int into a string, and the text node in HTML wants to have a string, of course, so we turn this number into a string. So if we uncover, did I make a typo? Yes. There's more places that I have to deal with. When we actually initialize the array in main in line 70, here I'm using this the empty variant of this type, but I'm not supplying it a number. So let's go here and say -1. And if we refresh now, then we see -1 on those fields. Awesome. So now what I want to do is, after we shuffled the bombs, because that's the moment in time where it gets the first time where we actually can calculate these numbers. There I want to right away calculate the surrounding numbers. So where is this happening? Where's our init function? It's here. Go to definition. Exactly. No, it's not the init function. It's the function, or it's the moment that we get the shuffled fields, I said. So here we have the fields. So instead of just giving them back, I also want to say calc the surrounding numbers, calculate. So I'm just going to calc surrounding, and it's going to take some fields and it's returning some fields. So we're just saying calc surrounding exactly fields. So currently it doesn't do anything, but it should at least still compile. Awesome. So that means we're going to touch each of the fields. So it's going to be a map. Calc surrounding bombs. That's the function that transforms each field into a new field, and we're going to give it the fields. And so let's write this as well. So calc surrounding, exactly. Go away, type annotation. This is taking a field. So, and again, we want to pattern match over the content, or over this field, over the content of this field. Field dot content. No, actually over both. So we want the content, but we also want the visibility. So in case I don't care if it's a bomb, I care about the visibility, then I'm just going to return the field. And in case, I don't care about the visibility, but it's an empty, and I don't care about the number that's stored currently because I know it's the -1, so I'm ignoring this as well. Here, maybe to do a minimal step again, field, I'm just saying content, partial update to our field record. Content is empty 0. So does this compile? It does not. Multiple surrounding. Ah yeah, I called this surrounding bombs, not surrounding. No. Surrounding bombs. Why don't you suggest that to me? Surrounding bombs. Content. Where's content? Content, of course. Does it compile? It compiles, so that means there should be zeros everywhere. Great. So now the next step is to actually update this number correctly. So how I would go about this is, if I'm looking at any given field, I want to calculate the coordinates of the surrounding fields. And then I want to check each of them if there's a bomb. So I think first of all, I'm going to calculate the locations of all the bombs. And then for each field, I'm just going to check whether those coordinates are in the list of coordinates for the whole of the bombs. So, so of course, if I calculate the bomb location, surrounding here, here in the surrounding bombs fields, I don't have the number of the bomb locations just yet. So I'm going to again create a local binding bomb locations. So basically, I'm going to filter the array to contain only the bombs. I'm going to remember which index that was, and then I'm going to turn these indices into coordinates. That's the grand plan. So it's going to be a list.filter. And no, I have to first remember the position of each field. So it's going to be an indexed map. And I'm going to, this is an anonymous function or a closure that gets this first argument, again, the index of the field, and then the field itself. And I'm going to turn this into a tuple where the index is in the front and then the field is in the back. And so now I could put brackets, let's do this for now, because now I want to filter this. So list, whoa. So I can call list filter with another filter predicate, another anonymous function where I make sure this is only bombs. Let's do this right away and then write this a bit more nicely. So here we have the index that I'm for filtering purposes not interested in, but we have the field here, and the field has some content. So if content is bomb, this is our predicate. So now we're calling list filter. Let's just look at the signature. The first argument is a function, also called a predicate, that takes just one item and returns true or false for it. Then it receives a list of these items, and then it returns a list of the items for those items that returned true for this predicate. So this is rather ugly, and that's where we can use a nice piece of syntax sugar from Elm, which is one of the pipe operators, which is, so obviously I'm thinking about this here from the right to the left. So I'm first creating this weird tuple list from all the fields. Oh, I actually missed the argument here, and then I'm using this result of this operation to give it to the list filter, and then there's thing in the middle, so it's really, really ugly. So I want to write it down in the order that I'm thinking about the problem, which I can when I write it like this. So this is the first thing, and then I'm going to pipe. That's why I have this, this little nice arrow symbol here, which is really just a pipe and a larger than symbol into this other function, and it's always going to use whatever is in front of this as the last argument for whatever follows it. So this way I don't even need this these brackets, and it reads really, really nicely. Index map, this operation goes into filter. So that means I end up with a list of tuples where I have in the beginning the index of the field that is a bomb, and then the field info that I'm not terribly interested in. So the last thing that I need to do is turn these into chords. So I'm going to map again a function called toCoords over the result of this filter operation, or actually I'm going to extract first only the index, which is I'm going to take the first element of this tuple first. Now I have just a list of ints, and I'm going to turn those into chords. Of course, the toCoords function doesn't exist yet, so I'm going to create a local function here. Chords takes an index, and so how do I know that the 50s field, like what coordinates this has? I have to divide it by the number of columns, and then add the number of the current column to that. It's basically integer division. So let's do this. So mod by is yes, mod by. Now, so we want to divide to get the x coordinate. We want to have like, yeah, the remainder of an integer division by the number of columns, so the width. So we want to divide by the width, and we take the idx, and the row is like just integer division without remainder, so it is idx divided by width. So now it gets interesting, because of course, as you can see, I don't have a width here. So actually we can make this a top level declaration. I have a good feeling we're going to need toCoords again, but we have to find out how we get the width into this. So for calc surroundings, we actually need the width as well. So, but the point is, here we only receive a list of fields. So I'm going to say like, oh no, I also want to know the width that these fields were initially constructed with, because there are several widths of fields that can lead to any array of n elements. So we are going to add a second argument to our got shuffled fields method here, and there where we construct it, here we actually do have the width. So we can give this width already to our got shuffled fields. So now got shuffled fields does need two arguments, but through partial application we actually can already attach the width to that constructor, so that later when our command for the shuffling gets executed, the shuffled list gets basically completes the function call to turn this weird zombie call here with like partially filled arguments into a proper message value. All right, this looks good. Let's see what the compiler has to say. I probably messed it up. Oh no, it just works. That is good. Calc surroundings toCoords, but we don't use the bomb locations anywhere just yet. So now we have the bomb locations. So to calculate the surrounding bombs for any given field, we definitely want to give the bomb locations already to the surrounding bombs function. And the neat thing again with partial application here is, like, already when we are calling, when we're evaluating this expression, we calculated bomb locations only once. We don't always recalculate for each field where the bombs are. So now we have the bomb locations, we know where we are. So let's first determine our own, like if we go here field by field and try to calculate the surrounding bombs, we want to know where we are ourselves. Chords, and we need the width again, and we also need our target index, I guess. Target index. So all things we don't have access to. So target index, I'm just going to put in front of here, and then we are going to expect to also get the width part passed in. And so we are going to do the same binding trick here. We're going to pass in the width already here, and we're going to expect the width for calc surrounding as well. Where's calc surrounding? And luckily we already added the width here, so we're going to give calc surrounding the width. We have the width here. We can pass on the width here. Perfect. And now we just need to get the target index somehow. So this can be simply achieved by using indexed map, which in addition to the field itself also gives us the position in the list. So now that means we can transform this position in the list to our coordinates. So let's say we are looking at this field now. We know it is at 4, 4. Or 3, 3 I should say, because it's 0 index. And now we just have to calculate the surrounding indexes. So these are all offsets by 1 either in the X or Y direction. So let's just create a list with all the relative positions around this. So we are creating a list of tuples. And so let's say we want to start out with the left top corner. So that's -1x, -1y. So it is -1, -1. Then we move 1 to the right. So that would be 0, but we're still at -1 in the rows on the y coordinate. And then we have +1 and still -1 in the y coordinate. All right. Then let's go one row down. Here we skip the middle part, so we start on the left again with -1, -1, but the same row. And then we don't do the middle one, so 0, 0 doesn't exist. We go straight to +1 and 0. And then we just go again, start in the bottom left corner. Here, that would be again x -1, but this time y is +1. Then with x 0, y is still +1, and then we have x +1 and y +1. So each field is surrounded like 3 by 3 as 9 fields. We don't look at the middle field, so that should give us 8 surrounding elements. So here we have 3 + 2 is 5 + 3 is 8. Perfect. Can bring this all into one line. So those are our relative coordinates. So now we have to turn them into absolute coordinates. So we can use our neat pipe trick again, and we say list map, and then we get a function with an x and an y, and to make those are each of these relative coordinates. So basically we have to add them to our target coordinates to get the absolute position of the field that we want to know about, whether there's a bomb there or not. So we take target x plus x and target y plus y. Okay, now after this we have the list of all the coordinates surrounding these fields. And now we have to look up. Well, if we are here in the top, we might actually try to access a negative field. So maybe we do like a little bounce check here. So we do a list filter. Let's call this inbounds. And let's define a little function here in bounds with a coordinate. And so x has to be larger or equal 0, and y has to be larger or equal 0, and x has to be smaller than width, and y has to be smaller than height. And we see directly we have a little problem because we do have the width, but we don't have the height. So we're going to expect the height here as well. We're going to go where we call this, and we're going to give it the height here as well. We don't have the height here either, so we are going to expect the height here as well. Then we're going to where we call this, and we don't have the height here either. So we're going to again introduce the height here as well. And then we're going to the definition of this, and we're going to add another int. And then we go where we actually construct this. And here we have to pass in the height as well. And luckily we do have finally the height here. So we closed kind of the gap. I could use a compiler to show me all those spots, but this way it's a bit faster. So inbounds, let's go back where we left off. Here the indentation is a bit weird. Boom. Inbounds, we have filtered inbounds, so now we have only coordinates that are actually inside of the board. And now we can finally check whether this is a bomb. So let's just also create a little local function, is bomb. And so is bomb again gets an x and a y. And now we basically have to do the inverse operation of two chords. So we have the coordinates, but we have to find out in our long array which coordinates, which element in our list, I should say, do these coordinates refer to. So maybe instead of, let's put this nicely here to idx with x and y. It's the inverse operation. So it is y times width plus x. So is bomb. First we say this is chords to idx, I called it, yes. Chords. Now we have the idx, we have, that is one coordinate, yes. So now we have a number, and now we want to know in this list of fields. We don't have the list of fields yet. So basically, let's just write it out. So list, and like I want to do an indexed access, which doesn't exist for lists. So how this is emulated, and I think we should probably well, we just go with the flow for now. So if I want to have the nth element in a list, then I just ignore the n elements and -1 elements before. So I can just say list drop, and then I take this index. So let's say I want to have the element with the index 1, then I have to drop one element and just look at what's left, the first element of what's left. So we drop this, and then we pass it into list head, which gives us the first element of the map. So, and if this is, I can just write it like this, and if this is like equals just a bomb, well, So the just is because list head might be called with an empty list, and in this turn, like if we just go to the actually I think it's probably very nice. Documentation extracts the first list element of the list. So exactly, if I call head with an empty list, I get nothing on. Of course, I do know that well, it's not impossible for somebody to call our application with 0, for width and height. So we have to kind of deal with this, but I also kind of don't care. So I say like there is only a bump if there's actually a field that has a bump. That's why I'm comparing with just something, but it's not just bump, it's an entire field. So we say visibility, and since we are calling this before anything has happened, it's very, very likely hidden. Visibility is hidden. And content is bomb. So list filter. So now actually let's move this into the let block. Num bombs. So now we have a list of coordinates. No, actually not, because we have not really said list head. We need to have this operate on a list of fields, and these fields we don't have here in the surrounding bongs function. So we are also going to pass that in. Fields. Fields we have here as well. So we just give it. All right. So now like we have the relative coordinates, then we turned them into absolute coordinates. Then we filtered all the ones out that are outside of the board. And then we're only keeping the coordinates that are actually pointing to a bomb. So now we just have to finally list.length. And now we can actually replace this 0 with num bombs. Boom. Does it compile? Probably not. I missed a bracket somewhere. It's not this one. It is this one. Width, height. I cannot find a height variable in line 32. Height. Here, height. It's the new Apple height. So width to IDX in 35. Yes, to index needs the width to work. And again, I'm just following the compiler to show me what I've overlooked. To IDX, yes, to IDX wants 57. 57 is here. To IDX, to starters, wants the width. List drop to IDX with coords. Boom, it compiles. So that means we should have numbers. Where is the bomb? There is the bomb. Not bad, not bad, not bad. Where are the bombs? Where are all the bombs? Maybe we use a few more bombs to get a few higher numbers. 15 bombs, why not? There we go. All right. Not bad at all. So here should be a bomb. No, 3 is correct. All good. Very good. So maybe next thing to have a bit better view is if we click a bomb to indicate that the game is lost, we just reveal the whole board. So now we have to step back a bit from all the pre-computation I've been doing. Here's the view. Where's the update function? I think it's a bit more up here, updates. So if we click a field, let's just start by calling this one. Oh, do we do? I think we're going to do, I don't know what I'm going to do. I'm just going to turn this into a top level function. So let's say reveal with board and idx. So let's write this function. Oh no, let's call it, because I think there's already a reveal function. Let's call it clicked field. Function names are lowercase. This takes an board and an idx. Board idx. So I think that should just compile. No, because availability. What did I do? Ah, because I'm calling the reveal function and not the clicked field function that I. So this compiles again, no change behavior. I'm not going to prove that. I'm pretty certain when it compiles that it also works the way that I want it to. All right, so now I want to say if we've clicked on a bomb, then instead of just revealing the one, reveal all. And now it gets a bit like we have to do lookups again. I'm really contemplating to switching to an array, but I also see that I only have 1 hour left. So I think I'm going to do this maybe in a follow-up stream or something. I'm just like looking up by dropping the head and then blah, 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 from a linked list is obviously not ideal. I probably should have gone with an array to start with. And it's actually not that hard to refactor this. Or maybe I just refactor it. So let's say the game state, instead of being based on a list, it should be an array. So init, instead of doing a list here, we just say array.empty. We're doing it the right way. So now init, and now of course it will complain about the fact that here's things are not lining up anymore. And since I haven't basically nailed down our types by writing types annotations anywhere, it gets increasingly hard for the compiler. Well, actually, compiled what? Oh no, I haven't saved it. So now it's saying like, ah yeah, there's one thing here, it takes arrays. But it takes lists, but it should actually be all arrays. So now we basically, I have to go through and replace all when we expect lists to expect arrays. I don't mind up until after the shuffling to work with a list, because that's only happening one. And then after the shuffling, I'm going to turn it into one big list. So got shuffled fields. That is calc surrounding. So here we do all these things, and then at the end we're going to use the pipe operator again. We're going to call array from list, and that's going to return everything this list into an array. But there are obviously a lot more places where we have to deal with this. So most notably the view function. This is wants to do a list index map. I don't know if there's array index map, but yeah, but then it returns just another array, and the diff really wants to have a list. So we are just going to call array to list. That will not work. Do I have an array index list? Let's have a look. That's an opportunity to show the nice documentation. Do we have indexed map? Yes. So we are going to do array indexed map. Now calc surrounding, this is off. Clicked for blah, 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 blah. Clicked field. Clicked field is still returning a list. So this should be array indexed map. Boom. And it compiles. Wow, that was fast. I thought I'd have to touch more things, and it's still, it just works. Yeah, awesome. Now I said I want to do the reveal all. Clicked field, let's go to the definition is here, because now we can say array.get, and a function that just takes an int and gives me the nth element of this, the number I specified, if there are that many items in the array. So we can just say idx of board. And so if this is just, so that means I actually found an element at that position. And this field has a this field has a content. So if content bomb, then reveal all, else do the thing we did before. And in any, if I don't find an element anyway, then we don't do anything. So now we have to do the reveal all function. Reveal all takes a board and returns a board. Board is our array, and we are mapping, and we get a field, and we're just going to say f partial update visibility equals visible. It's not even worth a line break. It's getting quite hot with the 100 lines already, I think, as it is. Reveal all, does this compile? It does not, because I forgot the closing parent here, and also I probably want to pass in the board. Indexed map reveal, whoop. Why you no want? Because I'm reusing, oh no, that's fine. This index map produces an array of things, yes, I think, but all previous reveal all needs to get the board, of course. So, that means if I manage to find a bomb, woohoo, I've lost. That's half of the game, right? All right, so that's pretty good. Then there's, I think, only two elements left. One is, and that's the most complicated, is if I click on an empty field, I want to reveal all the surrounding empty fields. Yeah, that's basically it. So this is probably going to what I spent the most of the time with. And then the only thing that's missing is that if I have revealed all fields that are not bombs, then I have one, and that should probably indicate it somewhere as well. So let's do it. So if if content is bomb. So actually I'm going to change this into a pattern matching, because we have a few things to look at here. So if basically it behaves differently, either if it's a bomb that I'm clicking on, or if it's an empty field that has one or more bombs surrounding it, or if it's an empty field that has no surrounding bombs. And this is usually, it just looks nice how this works when you use a pattern matching, a case statement here. Case, let's just indent right away correctly. Content off. If it's a bomb, then I do the thing. Boom. Reveal all. And then we have empty 0. Profit. And in any other case, just, whoops, In any other case, just reveal the current field. Right. That should compile, right? Does it compile? It does not. Ah, yeah, because profit. That makes a lot of sense. So this is a bit more complicated because, like, basically, if we say, let's start out here in the lower left corner, like, we want to, if we are on an empty field, we're going to reveal all of the direct neighbors. So up and down and left and right. And if these are also have 0 surrounding bombs, then we want to continue doing this, which smells a lot like recursion. Maybe there's a less recursion way where we just shoot rays and it sounds complicated and it's 100% premature optimization. So we're going to stick with the recursive solution here for now. Alrighty. Empty 0. This should be. I'm not sure why this. It didn't compile in the first place. So basically, what are we doing? So I would say first, with current revealed, we should absolutely reveal ourselves first. That's something that we already know we definitely have to do. So now we have a board where we self. So this one here, let's assume all of this is still hidden, and we click on this one. We want to reveal ourselves first. And then with this new board where this is revealed, we want to call the reveal function basically on the direct neighbors. And it's important that we have revealed ourselves first, because otherwise we get an infinite loop. So what are the neighbors? Neighbors, we can do something neighbors we've done before, which is first we calculate the relative coordinates of the neighbors, which is very similar what we do with the surrounding, but it's a lot less because we don't look at the diagonals. So let's start on the left. So x minus 1, y is 0. Then let's go to the top, x is 0, y is minus 1. Then let's go to the right, so x is 1, y is 0. And one below is x is 0, y is 1. So now we have the relative coordinates, and now we want to turn them into absolute coordinates again. So we're going to, again, pipe this into a list map, and we're going to get these relative x, or let's call them dx, it's a tuple still, dx and dy, and we have to first know where we self are, so we have to, again, let's call it tx and ty is 2 cohorts of our current index here, idx, and 2 cohorts also wants width. So this is going to be interesting, but I'm going to follow my train of thought here first and calculate the absolute coordinates of the direct neighbors. So tx plus dx and ty plus dy. Boom, those are my direct neighbors. And now I basically want to call the clicked field for each of these neighbors. And so I could call list map with clicked field, but then I get 4 different boards where each of the respective absolute things is revealed, which is not what we want. We want to reveal them one by one and then, like, each time propagate the changed board through these calls. So this is done with list.fold. In Ruby, it's inject. In JavaScript, I believe it's reduce. They all do the same thing. And let's call this, if they take a folding function, let's call it the folder as a placeholder for now. And then they take the starting point with current revealed, and Then the last argument is the things over which we want to iterate, which is the last argument of the fold here, which we get through the piping, which are the list of the absolute coordinates of the direct neighbors. So with current revealed, does this make sense? And we probably also want to do an inbounds check, I guess, so that we don't run out of the... Let's do this, list, filter, inbounds. And I think we have a function like this already, like where's it defined? Inbounds is here. And it needs a width and a height. So we can just add those to it, width, height, and turn this into a top level function. Boom, and then we can reuse it. Here's it. And now when we call it inbounds, we also have to give it width and height. And now if we jump back to our reveal problem, here we can also just say width and height, which we still don't have in clicked fields, so the pressure gets higher to introduce, but I just, as I said, want to finish my train of thought. So we calculated the relative positions of the neighbors. We turned them into absolute. We yeeted all the coordinates that are outside of the board, and now we want to fold each of those coordinates to see to reveal them if they're also empty. So can we call, ideally what I want to do is I just want to call clicked field recursively. The thing is, clicked field requires a board, which is great because the folder function gives the last board in the iteration already as a first parameter to this function, but the second one is an index and not coordinates. So what we don't have to do before we call this recursively, we have to list.map to idx, and to idx is a function that needs width as well. So let's give it width, boom, clicked field. So neighbors, those are the neighbors, and that's actually not neighbors. That is actually the result of this huge expression is directly the altered board. So we can just put this here. And now we just have to make sure that we get width and height as well. So where do we call? So normally I would say like, maybe we just put them as parameters in here as well. Where do we call clicked field? But the thing is here, we don't really have this information in our update function neither. So I think I just want to store the dimensions with the board itself. So currently it's just this array, but I'm going to turn this into a record that also stores the width and height, and that might actually make the code overall a bit simpler as well. So where do we do this? Calc surrounding, here is where we calculate basically the initial, that's not true. The initial game state is of course calculated in the init function, which is here. So now here, let's call this fields is this empty array. Width is width and height is height. Boom. And now again, of course, everything table flip. It will complain about the fact that we have changed the game state type yet again after I fix this missing parentheses. width. I cannot find the width. Yeah, of course. 2 chords. So what I want to be able to do is basically say board.width, board.height, board.width. Let's see. 42 here as well, board.width. And now this is not a record, this is an array. So yes, it's starting to grasp what we're doing here. So basically we have to say like, oh, what we are passing here into click field, this should really be the string with fields and width and height. Let's go back. What is this? This is board. Board is our game state. So why does it expect this weird thing? Well, this is like, it kind of tries to reason from what we've returned. Again, because I didn't write any type signatures, it has to kind of follow the code and see what fields we're setting and returning values, blah, blah, blah. So again, this would be a lot simpler if I had written type signatures, but again, I'm just, for the sake of proving that I don't have to, I'm just not doing it. So let's go into calc surrounding. Here we are calculating these fields. Let's just call them fields. We are just going to assign this to a nice identifier, and then we are returning fields equals fields, and we have width equals width and height equals height. Boom. So what's next? Again, it's not happy. Fields, let's call them fields with surrounding. Yes, boom. All right, and then again, I want something I can call .width of, but I only have an array. Line 42. Board, that's still in clicked field. So let's make sure first of all that all our branches in the update actually return the correct function, the correct structure. Reveal all. What does reveal all? Is array map. So that's already not great. So we want to take the board and only update the fields with array map and board dot fields. So nothing, that's correct. And here again in array indexed map. So here we want to say again board fields is board dot fields. And now we're getting closer. All of this list and map and fold stuff. Clicked field. Oh, this should actually work. Let's see how far we are. Reveal all board 39. And so this is basically the type signatures that Elm is inferring, that I can have the LSP display for me. And it gets really unwieldy as soon as you don't have proper type aliases for those record types. And then fields and fields. That doesn't look too bad, but somewhere we're missing just content board. This returns board. And what does got shuffled fields? Is this already calc surrounding? Gives me something with width, height, and fields. Last arrow is here. Fields, width, height. So this looks good. Reveal all fields. And what do we passing in here? Yeah, this is only the array, so that's wrong. So let's just comment this out for briefly to see debug.todo, where else it falls apart. Board width still here. Ah, no, here with current revealed, this also has to be a board. Board fields equals board dot fields, of course. I think here now we can throw, because basically the first branch it finds where it can determine the type, that's the type it expects for all other branches as well. Boom. Nope, still not happy. Board. This is not a record. Why are you? Why? It's a record. Trust me. It's a record. Trust me. Ah, maybe view. View. Yeah. Maybe actually view is the first one. View has a field called fields. So this expression basically is I'm destructuring the fields inside of this record. So in view, I'm only interested in the fields. So I don't have to write board.fields in the end here, but I can just say like, just take out the fields field from this board. And it's still unhappy. This is an array. Why is this still an array? Clicked fields. Board.fields. Of course. All right, now we're getting somewhere. So now we can, so basically because I said like array get and this takes a board, it inferred that board must be an array, and that's why it was screwed up everywhere else as well. Well, again, type signatures help, but for the sake of brevity, we're omitting them today. So now with current reveal, now this is getting into more interesting territory. 49. So map to IDX, so this should be a list of integers. Clicked field. Yeah, that's not very helpful. With current revealed is a fields, yes, this is a board, basically what it does want to say me, but fold L needs the second argument to be an int. What? The second argument should be the board. Why though? Clicked field, so it fold L iterates over the list of integers. Let's go back to the fold L. So a list of A is the integer. The order is the wrong way around. So we want to basically invert those. That also means, of course, wherever we're calling them, it has to be inverted. And now it's compiling, which is pretty amazing. So that means if we go here in the corner, and of course I click a bomb immediately, maybe we reduce the number of bombs again. Boom. Then, of course, too much recursion. The dreaded too much recursion. Yes, that's the one thing I wanted to avoid, but of course, you don't get to. You have to pay your dues. This is clicked field. We don't want to always recurse into those, or do we? Reveal. We only want to reveal them if they're... but they have to be empty. So if I'm here and I'm empty and these are empty as well, even if they contain like the numbers 111, I want to reveal this one. And then I want to, no, I only want to reveal them if they're empty. If I only want to reveal them if they're empty. So I have only, I After my inbounds check, I also want to filter, I want to map them to an index, and then I basically want to say like list dot filter is empty basically, but I'm going to declare this inline. So I get an IDX, and I'm going to look up array get IDX from the current board. No, from with current revealed. I think it doesn't really matter. Oh no, it does. Otherwise I'm getting another infinite recursion. With current revealed. And if this is just, and then we have maybe I just is empty, and this is with current revealed. Please autocomplete, thank you. Or not revealed. That's why I want to have autocomplete, because otherwise I'm just messing it up. So, and with, actually I don't need to pass it in if I declare this in line here, or in this let block I should rather say is empty is array dot get IDX IDX from no, it has to be part of my with current revealed. I knew this would be becoming the neck breaker for this stream. So when I'm clicking the field, but if I click on an empty field, then the surrounding fields cannot be bombed. So it should be fine to just reveal them. Reveal, if it's not, this should be fine. Why is there an infinite recursion happening? And reveal, also this is horrendously inefficient. Here we can also just, let's rewrite this thingy. This shouldn't be the cause at least, but it can be basically replaced with an array set. So let's force reveal call this, or individual reveal, or let's just call it reveal. Reveal takes target and a board. And then we say case array get target board dot fields of just field, then do something, nothing, we just return the board. Field, then we do a partial update of the field. Visibility. Visible. And we say array dot set target this guy. So now we can, when we call reveal, we just say, this gets a lot easier. Reveal is now actually works on the whole board, right? Just returns a board. So this gets a lot simpler. Reveal IDX board. With current revealed is the same thing. Reveal IDX board. Goody, goody, goody. With current revealed. And I guess it compiles, but it still has recursion is empty. I haven't defined is empty. Ah, yeah, okay, is empty IDX is case array get IDX of with current revealed of just f, then we can just is empty content, and we just say content is not bomb. If it's nothing, then it's definitely not a bomb. Boom. IDX I have defined twice, so let's call this IDX underscore and content is also already destructured here, so I have to give this actually field.content. Nothing board in line 100. Board field, just updating the field of our board. And here we have to say board.fields, of course. All right, with current revealed 45, current dot fields. Wow. All right, and where's a 0? Give me a 0. Bam, too much recursion. Damn. Up, down, left, right, yes. Then we are translating this into absolute coordinates. I'm making sure it's in bounds. Reveal IDX bounds is empty. I said we don't need this empty anyway, because fields surrounding an empty 0 are always empty. Okay, let's do something really stupid and just make an empty field with just 2. So no bombs. Boom. Too much recursion. I have no clue why this is not displayed. Because that's also an interesting thing. Yeah, I haven't addressed yet that we need to adjust the grid template columns here. There's a neat trick with CSS variables that we can do. But I really like, damn, it's so tight with the time, 17 minutes to crack the damn recursion error. Those are the hard ones. If somebody's in the chat and wants to give me a hint, I'm very welcome for hints. So inbounds. Yeah, I said clicked field. Let's just, for my sanity, also let's just set this to 2. So now we have 2 by 2. I'm clicking one and then it goes to the, let's just see what the stages are of these. Clicked field to coordinates, board.width, idx, this is all fine. Inbounds. Clicked field, that is good. With current revealed. Ah, no, we have to also, have to select on the visibility, because if it's already visible, we don't want to, yeah. Oh yeah, I got it. Clicked field, we can just have an early return, basically. Just content dot visibility, if visibility equals visible, then board, else this guy. I think that's it. Boom. Yes. Whew. Close catch. So let's do this. 10, 7, 5, sure. Boom. Look at this. That looks more like it, right? Okay, nearly there. Now the thing that I wanted to address is, like, we want to make this grid dependent on the width. So let's use a CSS variable here. How do we get the CSS variable here? Well, very easy. We go to our view function, and to our board, we render a style attribute. Yes, style, and then we say minus width is 10. Let's say. Let's save everything. This looks good. And now we say, no, it's actually, this is already, it should be already 510. So this is actually still hard coded. But if we say 5 here, then we should get a different grid. Exactly. So now we just have to replace this hard coded number with string from int width, and destructure the width here as well. Boom. So now I guess, I don't know, 3, 7. That's odd. Why is it 7 times 7? Also, what is that song? Let's not listen to that. All right. Let's look at the grid here real quick. Width 7, so that's correct. Why is it? I thought it's, oh no, the first one is the number of bombs. Okay, width is 3. Yes, baby. All right, so let's go back to something larger. Boom. So the only thing missing for 12 minutes to solve is to display a message that we have uncovered all the fields. So And the fun thing is, like, if I've noticed this in the Ruby solution of Radan, is that this is a property, something that has to be set on the board or something, but actually it's included in our data. It's like if the number of fields that are not revealed is equals the number of bombs, then we have one. So we actually don't need to store any additional information anywhere. We can just go into our view function, and I'm just going to wrap this in another div so that we can have a place where we show this message. And here we say if num bombs equal num hidden, then text u1, otherwise an empty text node. Or maybe we put this into a no, we'll just leave it there. So does this compile? It does compile, but we don't, it does not compile because we haven't num hidden and num bombs. So num bombs is array filter something over fields probably, and this function for every field we can just deconstruct the content. If content is a bomb, then that's the case, and for num hidden we do something very similar. But we have forgotten to, I have forgotten to pipe this into array dot length. We need to do this here as well, but instead of looking at the content, we're looking at the visibility. If, what did I say? Hidden fields are equals num hidden. Yeah, that's hidden, and then he goes and types visible. Yeah, that's the maximum duration for a stream that I can do. I think 2.5 hours. So let's inline those a bit more here. Boom. Does it compile? It does not compile. Why not? I cannot find a content variable. Ah yeah, because I have to check the visibility. Visibility. Boom. Does it compile? It compiles. Wonderful. So now, well, actually, let's change the rendering a bit as well. If it's empty and 0, then we just render an empty div. So, okay. 1. That's interesting. Here's. You won! With 8 minutes to spare, I would say I implemented a fully working version. So now what we can do is can make this a bit nicer, give this class hidden, import class, or actually no, I will do something else. First we want to see, of course, if we hit the 100 lines. I'm pretty sure I'm still over it, so I have to golf a bit more to actually get to below 100. First I'm going to resolve the duplicate imports here. And this looks all good. And again, of course, I could just hit auto format here, but then it would actually create a lot more empty lines, because it's actually nicer to read if there's more white space, obviously. but let's just see where I can squeeze out a few lines. Let's just say like this can be here on the first line. I don't even know. Let's just, although I think clog doesn't count empty lines anyway, so it's not really worth deleting empty lines. You can just, okay. So let's see, 100 lines net. But if I say clog source main, 94 lines. I'm pretty happy with this. All right, so of course I cheated a bit. The HTML is not included in this, but I would argue that's not actually part of the program. That's more part of the decoration. So yeah, I think I can claim I've implemented this successfully in my 2.5 hours time given a Minesweeper clone in Elm. Yeah, last step is of course publish it, git add everything, git done, git push. Of course you can go and look at the solution yourself. Maybe I do a bit of a cleanup later on. And as I said, like this is not the style that any M developer would actually develop this. There would be more type aliases, especially for the board type. But this has zero, as you can see, like writing the type annotation says 0 runtime impact or compile time impact. I'm not sure about this. It probably takes a bit longer for the compiler to figure out the types instead of me just telling them. But nonetheless, I don't need types in Elm or write type signatures when I don't want to write them out. So thanks for following me for all that time. I hope if I'm going to upload this on YouTube as well, and I hope you watch it at least at 1.5. But this was a very fun experiment for me. Yeah, thanks again for Radan for inspiring me to do this, and I hope I can inspire a few people with this as well. So thanks again, and see you next time.